CIET NCERT presents audiobook Ganit Manjari Part 1, Textbook of Mathematics for Grade 9.
Chapter number 7, The Mathematics of Maybe, Introduction to Probability, page number 155. On the top right corner of the page, you are provided with a QR code, scanning which you can reach out to the additional resources. 7.1. What is probability? Probability is a type of measurement similar to how we measure quantities like length, area, or volume. However, instead of measuring physical quantities, probability is used to measure the likelihood of events. Specifically, it helps us express how confident or certain we are that a particular event will occur. For example, you may ask your friend, "Is it going to rain today? Will our school win the inter-school hockey match tomorrow? Will I be chosen in the monthly lucky draw to perform at the school assembly?" The names of all the students in school are written on slips of paper and one slip is randomly selected. These events are examples of random events. We know the possible outcomes. Either it will rain today or it will not. Our school team will either win, draw, or lose the hockey match. One student will be chosen to perform at the school assembly, but we do not know in advance which one will definitely occur. That is, there is an element of chance or randomness involved every time such an event takes place. Can we predict these outcomes with 100% certainty? One could respond to these questions with words such as impossible or certain, or using phrases such as less likely, more likely, or equally likely. This decision is based on different kinds of evidence that have been gathered. For example, one friend might say, "The sun is shining brightly, so it's unlikely to rain today." While another might observe, "It's very hot, which makes me think it could rain later." In both cases, they are predicting rainfall based on how they interpret the present weather conditions. This is the subjective probability given to the event of today's rainfall. Page number 156. As you can observe from the above example, probability deals with uncertainty or chance. One key feature of our increasingly complicated society is that we must deal with questions that have no fixed answer, but rather one or more possibilities for the answer. Thus, understanding how to objectively estimate the probability of events is crucial in many aspects of life. In this chapter, we will learn how we can measure probability more objectively, that is, the ways of collecting evidence that can be used for an objective estimate of likelihood. But first, we must understand a few terms and ideas such as randomness and the probability scale. 7.1.1. What is randomness? Randomness refers to a situation or action like the tossing of a coin or the rolling of a die, where you cannot predict exactly what will happen. Although you may know all the possible outcomes, you cannot say which one will definitely occur. For example, tossing a coin, you know it could be heads or tails, but you cannot be sure which one will come up in a single toss. Rolling a die, you know the possible outcomes are 1, 2, 3, 4, 5, or 6. But you do not know which number will appear on a particular roll. These observations, commonly called experiments or trials in probability, are called random because of their unpredictability. The lucky draw example mentioned earlier is an example of a random observation or experiment, as the outcome cannot be predicted in advance and each student has an equal chance of being selected. All you can say is what could happen, not what will happen. Random observations. A random experiment is something you can repeat, like tossing a coin, where every time you do it, the result might be different and you cannot know the outcome in advance. Think and reflect. Such unpredictability can be useful sometimes. For example, in a cricket match, the fact that a coin is tossed to decide which team will bat first is considered to be a fair method. Can you explain why? Probability is the area of mathematics that studies randomness and how likely a specific outcome is to happen in a random situation. Page number 157. For example, when you toss a coin, the probability for heads is 1 upon 2 and for tails is 1 upon 2 because each is equally likely. In a random experiment, every outcome has a chance to occur, but you can only determine the likelihood, not the exact result. Have you wondered what makes an event like rain random? An event like rain is considered random because it depends on many complex factors in the atmosphere, such as temperature, humidity, wind patterns, and pressure, and is so sensitive to these factors that it is impossible to predict it with total certainty. Thus, it is impossible to know with absolute certainty whether it will rain on a specific day. Randomness in rain means that while the exact timing and location of rainfall cannot be predicted perfectly, we can estimate the likelihood or probability of rain in different locations based on patterns and probabilities derived from data. Think and reflect. Ask your friend to predict the outcome of a 1 rupee coin you toss. Do you notice that your friend could guess heads or tails but could not know for certain? That's randomness. All possible results are known, but each individual try is unpredictable. 7.1.2 The probability scale. Probability is measured on a scale from 0 to 1 to indicate the likelihood of the occurrence of an event. If the probability of your school winning the hockey match is 0.75, that means there is a 75% chance your school will win. This means that it is more likely than not that your school will win the match. If the probability of your school winning the hockey match is 0.5, that means there is a 50% chance your school will win. This means that it is equally likely that your school will win or lose the match. On the other hand, if the probability is 0, it could mean winning is impossible For example, winning without playing. And if the probability is 1, it could mean your school is certain to win. The probabilities of most events fall somewhere strictly between 0 and 1, expressing how likely they are to happen. Imagine a deck of 6 cards, where the number of purple and green cards is unknown. The probability of picking a purple card from the deck given here in figure 7.1 can range from impossible if there are no purple cards to certain if all 6 are purple. Page number 158. As the number of purple cards increases, the likelihood of selecting a purple card moves smoothly along the probability scale from less likely to even chance to more likely. This scale helps us understand and compare how likely different events are, just like using a number line. Here we are provided with a picture in which we have figure 7.1, probabilities of picking a purple card from a deck on the probability scale. The picture reflects the different possibilities like impossible with 6 green cards, less likely with 5 green cards and 1 purple card, even chance with 3 green cards and 3 purple cards, more likely with 5 purple cards and 1 green card, certain with all 6 cards of purple color. Here are a few examples of events and the probabilities of their occurrence. Observe the examples against the probability scale in figure 7.1 to understand how probability is measured on a scale. We have a tabular column. In the first one, we have the event, and in the second one, it explains what it means. First one, getting a number greater than 6 on a die. It means it is impossible. Dice only have numbers from 1 to 6. Second event, rolling a 3 on a standard die. It means less likely, but not impossible, as one face of the die is 3. Third event, flipping a coin and getting heads. What it means? Even chance. Heads or tails are equally likely. Page number 159. The event is drawing any number from 2 to 10 from a deck of 52 cards. What it means? It means more likely. There are 36 cards in a deck of 52 cards with numbers from 2 to 10. Next event is choosing a red sweet from a bag of all red sweets. It means that it is certain event. All the sweets are red. Exercise set 7.1. Question number 1. Rank the following events on a scale from 0, that is impossible, to 1, that is certain. Label each event impossible, less likely, equally likely, even chance, more likely, certain. Give reasons why you gave each event its ranking. First part, the next Monday will come after Sunday. Second one, it will snow in Mumbai in July. Third one, an elephant will walk through your classroom today. Fourth one, you will greet at least one friend at school tomorrow. 7.2. Measuring probability objectively. There are two main ways of estimating the probability of an event objectively. First, using evidence from experience. This involves collecting data either by performing an experiment multiple times or by analyzing statistical data from past observations. In both cases, the probability is estimated by calculating the relative frequency of the event based on the collected evidence. We call this experimental probability. Second, using theoretical methods. This approach assumes that all possible outcomes are equally likely when there is no reason to believe that any one outcome is more likely than another. The probability is then determined by reasoning about the number of favorable outcomes in relation to the total number of possible outcomes. We call this theoretical probability. Page number 160. 7.2.1 Experimental probability, performing observations or experiments. Another way of obtaining objective estimates for probabilities is to perform an experiment. In an experiment, the event is a result of the experiment and is called an outcome. The set of all possible outcomes in an experiment is called the sample space. The sample space may be listed within brackets, separated by commas as given here. Example 1. Experiment. A coin is tossed. Possible outcomes are heads, that is H, or tails, within brackets T, as given in figure. So sample space is within brackets H, T. Experiment is a die is rolled. Possible outcomes are the top side of the die gives 1, 2, 3, 4, 5 or 6 dots, as given in figure 7.3. Sample space will be within brackets 1, 2, 3, 4, 5, 6 within brackets. Here we have two pictures. In figure 7.2, heads and tails of a coin are given when we are tossing the coin. In the next picture 7.3, we have in the figure a six-sided die with the dots visible to us as 6 on one side, 3 on the top side and 5 on the side. Experimental probability is equal to number of times the event occurred upon total number of trials. Example 2. Suppose you roll a die 50 times and it lands on a 4 exactly 8 times. Experimental probability of rolling a 4 is 8 upon 50, that is equal to 0.16 or 16%. We also say that the relative frequency of rolling a 4 is 8 upon 50, that is equal to 0.16. Relative frequency helps you understand probability based on actual data rather than theoretical predictions. It is especially useful in statistics and data analysis when you are working with observed outcomes. Page number 161. Did you know the game of snakes and ladders originates in ancient India? It evolved from a traditional dice game called Gyan Chopper, which was used as an educational tool. Gyan Chopper aimed to convey moral lessons, with each ladder symbolizing a virtue and each snake representing a vice. Through gameplay, it illustrated the consequences of good and bad behavior. Various versions of Gyan Chopper have been used in different parts of India. Here we have in figure 7.4 a Jain Gyan Chopper game on cloth. National Museum, India of 19th century. We have a picture reflecting the snakes and ladders with numbers depicted on it. 7.2.2 Theoretical Probability. Theoretical probability studies the likelihood of an event happening based on all possible outcomes being equally likely. It is what we expect to happen in an ideal, perfectly fair situation. In this scenario, no experiment or data is required. Theoretical probability is usually denoted by P within brackets event or P within brackets outcome. Theoretical probability within brackets P is equal to number of favorable outcomes upon number of possible outcomes. Example 3. If you roll a standard 6-sided die, what is the theoretical probability of getting a 4? Solution: number of favorable outcomes is equal to 1. Within brackets only the number 4. Number of all possible outcomes is equal to 6. Within brackets the numbers 1 through 6. P within brackets rolling a 4 is equal to 1 upon 6, that is equal to 0.1666 and so on. That is approximately equal to 0.167 or 16.7%. Example 4. A letter is picked at random from the word probability. What is the probability of picking the letter B? Page number 162. Solution: number of favorable outcomes is equal to 2. Within brackets there are 2 B's in the word probability. Number of all possible outcomes is equal to 11. Within brackets the number of letters in the word probability. P within brackets picking the letter B is equal to 2 upon 11, that is equal to 0.1818 and so on, is approximately equal to 0.182 or 18.2%. 7.2.3 Analyzing statistical data using probability. The way of collecting evidence through statistical data is used extensively in the world of business for marketing, forecasting sales, insurances, and in science and social science research. Example 5. Suppose you anonymously collect information regarding the favorite fruit of 50 students in your class. Let us assume that the results are 20 students like mango, 15 students like apples, 10 students like bananas, and 5 students like grapes. Let us play a game. Suppose we randomly pick one student from the class and try to guess their favorite fruit. What's the probability that the student's favorite fruit is mango? Statistical probability is based on collected data. So, a reasonable estimate that the student's favorite fruit is mango is probability of mango as the favorite fruit is equal to number of students who like mango upon total number of students, that is equal to 20 upon 50, which is equal to 0.4. So, there is a 0.4 of 40% chance that a randomly chosen student in the class likes mango. Now, assume that you want to buy fruits for the entire school depending on the student's favorite fruits. You would need to estimate the quantity of each type of fruit you need to purchase for the entire school, or say 1500 students. It is usually impractical to collect data from all students or the entire population. The application of statistical probability in the real world is usually based on evidence collected from a sample. The population, that is, the total number of students in the school, is 1500, and we collected evidence from a sample of 50 students from one class. Page number 163. An estimate of the probability that mango is the favorite fruit was collected to be 0.4. So that would mean that we need to buy approximately 600 within brackets 40% of 1500 mangoes, while the remaining would be other fruits, apples, bananas and grapes. If we want to be more confident about our estimate, we would choose a larger sample, for example, by asking 100 students, and make sure it is more representative, such as including students from different classes or grades. This process is called sampling in statistics. Learn more about sampling. Want to learn more about sampling? What we have learned so far is just the beginning. When collecting data through samples, there are other important things to think about, like how big your sample should be or how to make sure your sample truly represents the whole population. The size of your sample and making sure it's fair and not biased can help your results be more accurate. If you are interested and want to explore more about why sample size and representation matter in statistics, you can read more about it in print or digital resources. Summarizing, experimental probability is based on actual data collected from trials, not on assumptions. Theoretical probability relies on the assumption of equally likely outcomes, a perfectly fair situation, and does not use experimental data. Even in perfectly fair situations, experimental probability can differ from theoretical probability, especially when the number of trials is small. As the number of trials increases, the experimental probability tends to get closer to the theoretical probability. This is known as the law of large numbers. Think and reflect. If I had rolled a 4 on a die 8 times in succession, the probability of rolling a 4 again is still only approximately 0.16, assuming the die is fair. Probability does not tell you what will happen next, but predicts what will happen in the long run. Page number 164. Gambler's fallacy. Many people think that if something random happens many times in a row, like flipping a coin and getting heads 6 times, then the opposite outcome, that is tails, is more likely to happen next. But actually, the coin does not keep track of what happened before. Every time you flip, the chance of heads or tails stays exactly the same, like starting afresh. The coin has no memory, no past flips, do not change what happens next. This common misunderstanding is called gambler's fallacy. For example, imagine that you are flipping a fair coin. It comes up heads 6 times in a row. You might feel that on the next flip you are sure to get a tail. because tails haven't come up for a while. However, the probability of getting tails on the next flip is still 50% or 1 upon 2, exactly the same as before. The coin has no memory of past flips. Example 6. Let us say you are playing snakes and ladders and you are rolling a fair six-sided die to move. You have just rolled the die 3 times in a row and each time you got a 6. Now you think, I have already rolled 3 6s. There is no way I will get a 6 again on the next roll. This thinking is gambler's fallacy because each roll of the die is an independent event. The probability of rolling a 6 is always 1 upon 6, which is approximately equal to 0.166 or 16.6%. It does not change based on what happened in the previous turns. Key idea: in snakes and ladders, as in many games of chance, each roll of dice is independent. The gambler's fallacy tricks people into believing there is a pattern, when in fact such randomness has no memory. Fair and unbiased. When we speak of a coin, we assume it to be fair, that is, it is symmetrical so that there is no reason for it to come down more often on one side than the other. We call this property of the coin as being unbiased. By the phrase random toss, we mean that the coin is allowed to fall freely without any bias or interference. Page number 165. Exercise set 7.2. Question number 1. A teacher mixes a large bag of sweets of different colors and randomly selects a sample of 30 sweets. She counts the number of sweets of each color: 10 red sweets, 8 green sweets, 7 yellow sweets, 5 blue sweets. First part, calculate the probability that a randomly picked sweet from the sample is green. Second part, if there are 600 sweets in total in the large bag, estimate how many are likely to be yellow based on the sample results. Question number 2. A survey is conducted at a school where a random sample of 40 students is asked about their favorite club. The responses are: 14 students prefer science club, 11 students arts club, 9 students sports club, 6 students debate club. Assume there are 800 students in the whole school. First part, what is the probability that a randomly chosen student from the sample prefers the arts club? Second part, using the sample results, estimate how many students in the whole school are likely to prefer the sports club. Question number 3. Toss a coin 20 times and record the result each time, heads or tails. First part, how many times did you get heads? Second part, how many times did you get tails? Third part, calculate the experimental probability of getting heads. Fourth part, if you toss the coin once more, what is the probability of getting tails? Question number 4. Toss a paper cup into the air 100 times. After each toss, record whether the cup lands on its bottom, upside down, or its top, or on its side, as given in figure 7.5. Assign probabilities to the outcomes by using experimental probability. Here we have in figure 7.5 a picture of a boy who is tossing the cup. Paper cup landing positions left to right, bottom, top and side are displayed here. Question number 5. What is the probability of getting an even number when rolling a fair six-sided die? Page number 166. Question number 6. Suppose you roll a six-sided die 12 times and get a 3 times. First part. What is the experimental probability of rolling a 3? Second part. What is the theoretical probability of rolling a 3? Third part. Why might these probabilities be different? What would you expect to happen if you roll the die 60, 600 or 6000 times? 7.3 Elements of probability, sample spaces and events. 7.3.1 Sample space. Recall that the sample space denoted by S is the list of all possible outcomes. Each possible outcome is called an element of the sample space. First point, the sample space S must include every possible outcome. Second point, no outcome should be listed more than once. Third point, the number of elements in the sample space is called the sample size and is denoted by n within brackets S. Examples of sample space. First one, the sample space for whether it rains tomorrow could be S is equal to within brackets rain, comma, no rain, and the sample size n within brackets S is equal to 2. Second one, the sample space for a match, that is, the possible outcomes for a team playing could be as S is equal to within brackets win, comma, lose, comma, draw, and sample size n within brackets S is equal to 3. Third one, tossing a coin. Experiment, tossing a fair coin once. Sample space S is equal to heads, that is capital H, comma, tails, capital T. Sample size is equal to 2. Fourth one, rolling a die. Experiment is rolling a standard six-sided die. Sample spaces S is equal to 1, 2, 3, 4, 5, 6. Sample size is equal to 6. Tossing two coins. This is fifth one. Experiment tossing two coins simultaneously. Sample space S is equal to within brackets HH, comma, HT, comma, TH, comma, TT within brackets. Sample size is equal to 4. Here on this page you are provided with a tabular column in which we have 3 columns, first reflecting coin 1, second coin 2 and third one reflects outcome. So in column 1 we have H, in column 2 we have H and in column 3 we have HH as the outcome. For the next row we have for first coin H, coin 2 we have tail T and in outcome we have HT. In the third row we have for the first coin T and for second coin it is H and the outcome is TH. And in the last row for coin 1 we have T, for coin 2 we have again T and the outcome is TT. Page number 167. Think and reflect. When we used the sample space rain, comma, no rain in example 1 we focused only on whether it will rain or not. However, if we want to include different amounts of rainfall like drizzle, light rain, or heavy rain, we need to expand the sample space to no rain, comma, drizzle, comma, light rain, comma, heavy rain, so that it better matches the level of detail required for the question. It is important to ensure the sample space is detailed enough to suit the specific problem being studied. 7.3.2 Events. An event is any single possible result or combination of results that might happen when you perform a random action. It is like choosing particular outcomes from all the things that could possibly occur. An event is a subset of a sample space. Examples of sample spaces and events. First one, tossing two coins. Sample space, all possible results like head, comma, head tail, comma, tail head, comma, tail tail. So S is equal to sample space, that is equal to within brackets HH, comma HT, comma TH, comma TT. The event is at least one coin reflects head. E is equal to within brackets HH, comma HT, comma TH. Second one, rolling a six-sided die. Sample spaces, all faces numbered 1 through 6. So S is equal to within brackets 1, 2, 3, 4, 5, 6. Event is the number rolled is greater than 4. So E is equal to within brackets 5, comma 6. Third one, picking fruit from a basket. Sample spaces, types of fruit you might pick. For example, apple, banana and orange. S is equal to within brackets apple, comma banana, comma orange. Event is picking a fruit that is yellow. So E is equal to within brackets banana. Exercise set 7.3. Question number 1. When a single six-sided die is rolled, what is the total number of possible outcomes in the sample space? Question number 2. For the following experiments, write down the sample space S. First one, rolling a die and tossing a coin together. Page number 168. Second one, choosing a random integer between -5 and +5. Third part, a box containing 5 green and 7 red balls. One ball is drawn at random. Question number 3. In a village fair, there are 3 popular snacks available: samosa, pakoda, and bhaji. For drinks, villagers can choose either chai or lassi. First part, list the sample space of all possible snack and drink combinations a person could choose at the fair. Second part, list the event selecting samosa as a snack. 7.4 Tree diagrams. A tree diagram is a visual representation used to list all possible outcomes of a multi-step experiment. A multi-step experiment involves a series of independent trials. For example, tossing a coin 2 times or rolling a dice 3 times are examples of multi-step experiments. Each branch of the tree represents a possible outcome, and branches split to represent different paths for subsequent events. A tree diagram is useful for, first point, visualizing multi-step experiments where each path from start to end represents one complete outcome. Second point, listing all outcomes of a sample space. So far in this chapter, we have seen examples of single step experiments. Let us observe an example of a multi step experiment. Example 7. Experiment is toss a fair coin 2 times. T diagram is given in figure 7.6. From a single point, draw a line to each of the possible outcomes of the first toss. From each of these outcomes, draw 2 lines to each possible outcome. Do you observe that the T diagram shows 4 possible outcomes? Hence, the sample space S is equal to within brackets HH, HT, TH, TT. Here in figure 7.6, we have a T diagram showing possible outcomes when we toss a fair coin twice. In the first toss, we have H and T, and in the second toss, we have H, T, and the outcomes are written as HH, HT, TH, and TT. Page number 169. Also, the theoretical probabilities of each outcome are mentioned on the branch representing that outcome. Theoretical probability within brackets P is equal to number of favorable outcomes upon number of possible outcomes. Let's consider the event of getting heads twice. This is represented by the outcome HH. Probability of HH is equal to 1 upon 4, that is equal to 0.25 or 25%. Think and reflect. Can you calculate the probability of getting one head and one tail? Exercise set 7.4. Question number 1. There are 2 fruit baskets, A and B. Basket A has 1 apple and 2 oranges. Basket B has 1 banana and 1 mango. You randomly pick one fruit from each basket. First part, draw a T diagram reflecting all possible pairs of fruits. Second part, list the sample space. Third part, what is the probability of picking 1 apple and 1 banana? Question number 2. Let us say that you have a box containing 3 red pens, 4 black pens, and 2 green pens. You pick a pen within brackets without noticing from the box and put it back. Then your friend does the same. First part, what are the possible outcomes of the pen colors? Can you draw a T diagram representing the possible outcomes? Second part, can you use the tree diagram to guess the probability that both you and your friend pick pens of the same color? End of chapter exercises. First one, fill in the blanks. First part, the probability of an impossible event is dash. Page number 170. Second part, the set of all possible outcomes of a random experiment is called the dash. Third part, the probability of an event that is certain to happen is dash. Fourth one, tossing a fair coin has a probability of dash for getting heads. Question number 2. In a survey of 50 students, 15 students said they liked football. The number of students who like football is 15 and the dash within brackets frequency / relative frequency is dash. Within brackets, fill in the fraction or decimal. Question number 3. Which of the following experiments have equally likely outcomes? Explain. First one, a driver attempts to start a car. The car starts or does not start. Second one, tossing a fair coin once. Third one, rolling a fair six-sided die. Fourth one, choosing a marble randomly from a bag that contains 3 red marbles and 7 blue marbles. Fifth one, a baby is born. It is a boy or a girl. Question number 4. Write the sample space and calculate the probability based on the given information. First one, 2 coins are tossed at the same time. What is the probability of getting at least one head? Second one, 10 identical cards numbered 1 to 10 are placed in a box. One card is drawn at random. What is the probability of drawing a card with an even number? Third one, a die is rolled once. What is the probability of getting a number greater than 4? Fourth one, a bag contains 3 red balls, 2 blue balls and 1 green ball. One ball is picked at random. What is the probability that it is not red? Fifth one, 3 coins are tossed simultaneously. What is the probability of getting exactly 2 heads? Question number 5. A bag has 3 candies, strawberry, lemon and mint. One is picked at random. What is the probability of picking a strawberry candy? Page number 171. Question number 6. A child has 2 shirts, one red and one blue, and 3 types of pants, jeans, khakis and shorts. List all the possible combinations of outfits consisting of one shirt and one pair of pants. Display your answer in a table format. Question number 7. A tire company records distances before replacement in 1000 cases. We have a tabular column here reflecting distance in kilometers and number of cases. In the first column, we have less than 4000. Number of cases reflected are 20. For distances between 4000 to 4001 to 9000 kilometers, number of cases are 210. For distances between 9001 to 14,000, the number of cases are 325. For distances more than 14,000 kilometers, the number of cases are 445 in this tabular column. Find the probability that a randomly chosen tire lasts. First part, less than 4,000 kilometers. Second one, between 4,000 and 14,000 kilometers. Third one, more than 14,000 kilometers. Question number 8. The letters of the word peace, P-E-A-C-E, are placed on cards. Leela draws a card without looking at them. First one, what is the probability that it is a P, E or C? We have 5 cards here with letters P, E, A, C and E displayed here. Second part, what is the probability that it is not an E? Question number 9. A game of chance consists of spinning an arrow as given in figure 7.7, which comes to rest pointing at one of the numbers 1, 2, 3, 4, 5, 6, 7, 8. And these are equally likely outcomes. What is the probability that it will point at first part 8, second part an odd number, third part a number greater than 2, fourth part a number less than 9, fifth part a multiple of 3. Here in figure 7.7 we have a colored disc with a pointer, and the disc has number displayed on it as 1, 2, 3, 4, 5, 6, 7 and 8. It has a pointer pointing at 2 in the picture. Question number 10. A basket contains 4 red balls and 5 blue balls. One ball is drawn and laid aside, and a second ball is drawn. Draw a tree diagram to represent the possible outcomes and probabilities. Use the tree diagram to answer the following questions. Page number 172. First part. What is the probability of drawing a red ball and then a blue ball? Second part. What is the probability of drawing 2 blue balls? Question number 11. I throw a pair of 6-sided dice. Write down an event that has a probability of 0 and an outcome that has a probability of 1. Question number 12. Write the sample space and calculate the probability based on the given information. First part. 2 dice are rolled. What is the probability that the sum is a prime number greater than 5? Second part. A bag contains 4 red, 3 green and 2 blue balls. 2 balls are drawn without replacement. What is the probability that both are of different colors? Third one. 3 coins are tossed. What is the probability that the first coin reflects heads and exactly 2 heads occur in total? Fourth one. A 4-digit number is formed using the digits 1, 2, 3 and 4 with no repetition. What is the probability that the number is even? Fifth part. A student takes a multiple choice test with 3 questions, each having 4 options A, B, C, D, with only one correct answer. What is the probability that the student guesses and gets exactly 2 answers correct? Question number 13. A box contains 4 balls numbered 1 to 4. Record a sample space using a tree diagram for the following experiments. First one. A ball is drawn and the number is recorded. Then the ball is returned and a second ball is drawn and recorded. Second part. A ball is drawn and recorded. Without replacing the first ball, the experimenter draws and records a second ball. Third part. What are the sizes of these 2 sample spaces? Question number 14. List the elements of a sample space for the simultaneous tossing of a coin and drawing of a card from a set of 6 cards numbered 1 through 6. Question number 15. 3 coins are tossed and the number of heads is recorded. Which of the following list is a sample space for this experiment? Why do the other lists fail to qualify as a sample space? Page number 173. First part. Within brackets 1, 2, 3. Second part. Within brackets 0, 1, 2. Third part. Within brackets 0, 1, 2, 3, 4. Fourth part, within brackets 0, 1, 2, 3. Question number 16. Suppose you drop a die at random on a rectangular region as given in figure 7.8. What is the probability that it will land inside the circle with a diameter of 1 meter? Here we have a figure 7.8 which reflects a rectangle, blue in color, of dimensions 3 meters by 2 meters. It also has a circle and a hand with a dropper is dropping a drop inside the circular region. Chapter Summary. First point, probability is a measurement of the likelihood of an event. Second point, probability is expressed on a scale from 0 indicating impossibility to 1 indicating certainty, representing the likelihood of an event occurring. The probability of an event E is denoted as P within brackets C, where P within brackets E lies between 0 and 1, that is 0 less than or equal to P of E less than or equal to 1. Third point, experimental probability is determined by conducting an experiment and is calculated as experimental probability is equal to number of times the event occurred upon total number of trials. Fourth point, theoretical probability is based on all possible outcomes in a fair situation, assuming each is equally likely. Theoretical probability of an event A is P of A is equal to number of favorable outcomes upon number of possible outcomes. Fifth point, a sample space is the list of all possible outcomes of a random experiment. It is represented as a set S is equal to within brackets outcome 1, comma, outcome 2 and so on outcome n. Sixth point, an event is any one or a group of possible outcomes from a random experiment. It is like picking results or outcomes from all that could happen. Seventh point, tree diagrams help us to list and visualize all possible outcomes of a random experiment. They also help us calculate probabilities of events related to random experiments. Chapter 7 ends here.
Ganit Manjari, Part 1. You were just listening to this audiobook, Textbook of Mathematics for Grade 9. Narration, Swarnlata Sharma. Sound recordist, Virendra Rawat. Assistance in production, Soumya Malik. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.